Hi everyone, I am Sam. Today we are going to talk about time. Before Einstein's insights, most people, including scientists, viewed time as a universal flow, the ultimate unshakable background against which all events occur. Space was simply the stage on which everything happened, an empty arena. If you and I watched a train pass by, we might disagree about how fast it seemed to be going, but we would still agree on how much time passed. The clock on the wall, we assumed, told the same time for everyone. Then came Einstein, a young patent clerk with a restless mind, who proposed that these everyday assumptions about time and space were simply not correct. He argued that time could be stretched or compressed depending on how fast you move, and that space itself wasn't a fixed container, but something that could be shaped by matter and energy. It's easy to picture Einstein now as that iconic figure, white hair going in every direction, pipe in hand, a wise and kind face. But in the early 1900s, he was just a young man working at a patent office in Switzerland, reviewing other people's inventions. In his free time, he thought about light and clocks and how a person moving very fast would see the world. At that time, one stubborn fact stood out. The speed of light seemed to be constant no matter who measured it or how they moved. Think about that for a moment. If you were running toward a beam of light at an unimaginable speed, you'd think that the light's speed relative to you should be greater than if you stood still. But experiments showed the speed of light didn't change. It was always the same. How could that be? To resolve this puzzle, Einstein did something extraordinary. He decided that the laws of physics, and most importantly the speed of light, had to remain the same for everyone, no matter how fast they were moving. If that were true, then something else had to give. That something else turned out to be our everyday understanding of time and space. He realized that time could not be an absolute ticking away uniformly for all observers. Instead, time was entangled with space, forming what he called space-time. Observers moving at different speeds could disagree on the length of an interval or how much time passed between events because their measurements of space and time were no longer independent. They were woven together. This set of ideas became known as special relativity, and while it might sound intimidating, it rests on a few simple principles. First, the laws of physics are the same for everyone, no matter how they move, as long as they move in a straight line at a constant speed. Second, the speed of light in a vacuum is constant for all observers. From these two assumptions, Einstein derived a series of surprising results. He showed that moving clocks run slower than stationary ones, at least from the viewpoint of someone watching them speed by. Also, moving objects look shorter along the direction they move, and what one observer calls simultaneous events might not be simultaneous for another observer who's zooming past at a high speed. This is the birthplace of some of the most famous thought experiments and paradoxes in modern physics. Perhaps the most well-known of these is the so-called twin paradox. Picture two twins on Earth, each the same age. One twin decides to hop in a spacecraft and travel near the speed of light to a distant star and back, while the other twin stays home. According to special relativity, from the perspective of the traveling twin, it might look like the Earth is the one zooming away and returning, so you might think each twin sees the other as aging more slowly. How can it be that both think the other is younger when they reunite? When the traveling twin finally returns, reality reasserts itself. The twin who took the journey and traveled at near light speeds will have aged less than the twin who stayed behind. The traveling twin might be, say, just a few years older than when they left, while the stay-at-home twin might have aged decades. This result is counterintuitive but follows naturally from the mathematics of special relativity. The paradox, part of the twin paradox, comes from misunderstanding the roles of the twins. You see, the traveling twin had to turn the ship around at some point, changing their frame of reference and experiencing acceleration. This breaks the symmetry of the situation. The earthbound twin remained in one inertial frame, no drastic changes in speed or direction, making their experience of time straightforward. Meanwhile, the traveling twin underwent a journey that forced them to switch frames. This asymmetry resolves the paradox, but the weirdness remains. It's a reminder that our instincts about how time and space should behave no longer apply when we approach the speed of light. Einstein didn't stop with special relativity. He knew that the world also included gravity, and he wanted a theory that described it in the same elegant, coherent way he had described motion and time. For centuries, gravity had been understood by following Isaac Newton's ideas. Essentially, gravity was a force between masses. Apples fell from trees because the Earth attracted them, and planets orbited the Sun because the Sun pulled on them through this invisible gravitational force. Einstein, however, realized that if you consider how light travels and how frames of reference work, gravity might look quite different. After years of intense thought, mathematical struggle, and brilliant insight, he came up with general relativity. In general relativity, gravity is not a force at all. Instead, mass and energy tell spacetime how to curve, and curved spacetime tells objects how to move. Picture spacetime like a flexible, stretchy fabric. If you place something massive like the Earth on it, the fabric bends. If you roll a smaller object nearby, it will follow the curve. This looks and feels like a gravitational pull, but what's really happening is just motion along a curved surface. One of the strangest predictions of this theory is that time also runs differently depending on where you are in a gravitational field. The closer you are to a massive object, the more slowly your clock will tick compared to someone farther away. Take two identical clocks, put one at sea level and another high in a tall building. The clock at sea level, deeper in Earth's gravitational well, will tick slightly slower than the one at the top floor. These differences are tiny, but they have been measured and confirmed. So here we have yet another mind-bender. It's not just motion that affects time, but gravity too. If you try to piece all this together intuitively, you might find yourself a bit dizzy. That's normal. Our human experience evolved in a world where speeds are much slower than light, and gravitational effects are subtle, so we never had reason to develop an intuition for these extremes. Yet, Einstein's theories have been tested over and over by observing starlight passing near the Sun, by measuring how clocks and satellites tick compared to those on Earth's surface, and by detecting gravitational waves rippling through the cosmos. Every test has shown that Einstein was, within our best measurements, correct. But just because Einstein's theories are extraordinarily successful, that doesn't mean they're complete. This leads us to another set of paradoxes, or at least puzzling scenarios, that emerge when we try to merge Einstein's picture of the world with that of quantum mechanics. Quantum mechanics is the theory that describes the very small, electrons, photons, atoms. It tells us that particles can be in multiple states at once, that outcomes can be fundamentally uncertain, and that reality at the tiny scale is nothing like the clockwork universe Einstein inherited from Newton. Einstein himself famously wrestled with quantum theory. He accepted it as a successful theory for predicting outcomes, but he was unsettled by its philosophical implications. In 1935, he and two colleagues, Boris Podolsky and Nathan Rosen, proposed what came to be known as the EPR paradox. They considered two particles that had interacted so that their properties were linked, or entangled. Even after the particles moved far apart, measuring the property of one particle, like its spin, instantly gave you information about the other. It seemed as though the second particle knew the measurement result of the first particle instantly, no matter how far apart they were. This appeared to violate the idea that no information could travel faster than light, a cornerstone of Einstein's own relativity. Einstein hoped this showed that quantum mechanics was incomplete, that there must be some hidden information traveling along with the particles that explained their correlated outcomes. He called it spooky action at a distance, and found it deeply troubling. Over the decades, however, experiments have consistently shown that there are no hidden variables that explain away this spookiness. Quantum entanglement is real. Particles do seem to be connected in ways that defy ordinary logic, and the results of measurements truly depend on each other in ways we struggle to interpret. This doesn't allow us to send signals faster than light, so it doesn't break relativity, but it does show that reality is even stranger than Einstein imagined. This tension between relativity and quantum mechanics remains one of the biggest puzzles in physics today. We have two grand theories: general relativity, which explains the cosmos on the grand scale of galaxies and black holes, and quantum mechanics, which explains the tiny world of atoms and subatomic particles. Both theories work extraordinarily well in their respective domains, but when we try to combine them to understand extremes, like the inside of a black hole or the very beginning of the universe, we find contradictions and confusions. Physicists have been searching for a unifying theory that can marry these frameworks, something often called a theory of everything. But so far, no one has found a solution everyone agrees on. This is not just a problem of mathematics or complexity. It's also a philosophical challenge. Einstein's insights teach us that concepts we take for granted, like time, space, and simultaneity, are not as absolute as they seem. Quantum mechanics pushes us further, implying that observation and measurement play key roles in determining what can be said about reality. When we stand back and look at the big picture, it becomes clear that our universe might be governed by principles far beyond our common sense understanding. Yet, it's not all about confusion and paradox. One of the great beauties of Einstein's work is that it shows how much can be understood by starting with a few simple postulates and following them through to their logical conclusions, even if those conclusions defy everyday intuition. The twin paradox, for example, is unsettling and counterintuitive. But once you recognize that one twin experiences acceleration and a change of reference frames, the solution falls into place. Similarly, the EPR paradox is mind-boggling, but it led physicists to a deeper understanding of quantum entanglement and to technologies that harness these quantum effects for cryptography and computing. Einstein's theories have also inspired new ways of thinking in more familiar contexts. Consider your smartphone's GPS system. To give you accurate location data, it must factor in both special and general relativity. Satellites in orbit move fast enough and are far enough from Earth's gravity well that time dilation effects become relevant. Without Einstein's corrections, the GPS on your phone would quickly become inaccurate. This is a remarkable example of how a theory that once seemed purely theoretical and philosophical now quietly underpins everyday technology. Reflect for a moment on the implications of all this. Since Einstein's day, we've come to realize that we live in a universe 13.8 billion years old, expanding, filled with billions of galaxies. Within this vast universe, time and space stretch and curve, and quantum fields fluctuate at tiny scales. Black holes lurk in the darkness, regions of space-time so warped that not even light can escape. Gravitational waves ripple through the cosmos as massive objects like neutron stars and black holes collide. Over the past century, we've learned that nature's rules are subtle, flexible, and sometimes seemingly paradoxical. All these ideas owe a huge debt to Einstein's original willingness to question basic assumptions. Before him, few dared to think time itself could depend on who was watching it, or that gravity might be geometry instead of a force. And while he was far from comfortable with the implications of quantum theory, his challenges to it forced us to think more carefully and do more precise experiments, which in turn deepened our understanding of reality's quirky nature. So, if you find yourself feeling a bit unsettled by these paradoxes and strange ideas, take heart. It's perfectly natural to feel that way. We are, after all, creatures evolved on a planet where speeds are slow, distances are relatively small, and gravity is fairly gentle. Our brains are wired to understand concepts like now, then, and next to, not space-time continuum, entanglement, and curved geometry. It's only by careful thinking, guided by experiments and observations, that we begin to glimpse the true complexity of the universe. In some sense, understanding Einstein's ideas and the paradoxes they inspire is an act of humility. They remind us that what we see is not always what truly is. Our senses and intuitions evolved for survival, not for cosmic truth-seeking. Yet we have, through human curiosity and ingenuity, stretched our minds far beyond their starting point. We have learned to translate complex mathematics into predictions, and then test them with careful experiments. We have developed new technologies that rely on these strange ideas, and we have pushed forward the boundaries of what we can imagine. The story doesn't end here. There are still countless mysteries waiting. What happens at the edge of a black hole? Can we unify gravity and quantum mechanics into a single coherent framework? Do we live in a multiverse, with countless other versions of reality branching off like an infinite tree? These questions might sound like science fiction, but they are the bread and butter of modern theoretical physics. And at the heart of all this speculation and inquiry stands the legacy of Einstein, reminding us that the path to understanding the universe often leads through questioning what we thought was obvious, confronting the strange, and learning to embrace the paradoxical. As you watch the sun vanish behind the horizon and the stars begin to appear overhead, you can think of the night sky not just as a backdrop for human stories, but as a dynamic stage where space and time intertwine. The stars you see may be shining from millions of years in the past, their light stretched and contorted by the expansion of the universe. The cosmic tapestry overhead is woven from curved space-time, sprinkled with the shimmering hints of quantum uncertainty. It's a place where intuition falters, but imagination and reasoning can still guide us. In the end, Einstein's work and the paradoxes it spawned are a testament to the power of human thought. We can challenge centuries-old assumptions and discover that the universe is stranger, richer, and more wonderful than we ever knew. And as we continue to explore, we may find even greater surprises waiting, just beyond the edge of our current understanding. That's all for today, and I'll see you in the next episode.